Good morning, everyone. Yesterday we were discussing about the basics of the IIR filter. Okay, so we have seen how the placement of the poles at different locations in the Z plane can result in the formation of or the designing of the filters which have different stabilities. So we have seen that if the poles are present within the unit circle, the filters are stable in nature. If the pole are on the unit circle, then they become marginally stable and the output does not either grow uh, out of bound, neither it will die down. Okay, so it will remain constant, right? And lastly, if the pole is outside the unit circle, then the output due to the input impulse input, it will grow out of bound at time tending to infinity. Now coming to the IIR filter design, uh, yesterday we have discussed that there are four types of IIR filter designing methods. The first one is the impulse invariant method. Second one is the bilinear transform method. Third one is the frequency transformation method. And lastly, we have approximation of derivatives method. The approximation of derivatives methods, it is not commonly used, but still we will be discussing it at a later stage, and we will see how we can design the filters by this method. Okay, and during the course of the this chapter, as we cover this chapter, we will find that bilinear transform method, it is the one of the most sought after method for the designing of the IIR filters due to the advantages it provides. Okay. Now, today we will first start with the impulse invariant method. In some textbook, you will find it is written as impulse invariance. Impulse invariance method. So both the method they are same. Impulse invariant method and impulse invariance method both are same. Similarly, in the second one, in some books you will find bilinear transform method, and in some books you will find bilinear transformation method. So both are same. Okay. Now coming to the impulse invariant method. So what is the advantage of this method? The advantage of this method is that it tries to emulate the information of the analog filter, okay, of the analog filter which are being designed in the S plane, okay, and it uses this information to figure out the position of the poles and the zeros in the Z plane. That means if you have any transfer function of an analog filter, that means if you have Hs of any given uh, system, then the impulse invariant method, it provides you the opportunity to emulate this analog filter, and it will provide you a method to design a digital filter. Okay, so while using this method, you have to be careful that the analog filter that you choose, that should be stable in nature. Okay, the reason being, what you are doing, you are emulating the analog filter, right? So if due to some reason your analog filter it is unstable in nature, then the filter whatever you will be designing, digital filter whatever you will be designing, it will also be unstable if your analog counterpart is unstable. So while choosing the analog filter transfer function, you have to be very careful while you are designing the digital uh, filters using the impulse invariant method, that it should be stable in nature. Okay. So what does this method says? This method says, suppose you are having a pole at 1 by s minus p1, then this analog pole, it will be transformed into 1 by 1 minus e to the power pit z inverse. Okay, pit z inverse. So we know that this equation 1 by s minus p1, it is in the s plane, that means it is in the analog plane. And in the second one, where we are having z inverse, we know this component, it is in the z transform or the z plane domain. So we know z plane is used for designing digital filters. So the impulse invariant method, if you see over here, it gives you a direct relationship between the analog and the digital domains, and thereby it helps us in creating or designing a filter quite easily. Okay, over here the capital T, in this case, it is basically the sampling period, and this sampling period, it is basically, we have already seen that capital T is equal to 1 by Fs. Usually when we design digital filters, we are given with the Fs, or in some cases we are given with the capital T time period. Okay. So if capital A is given, you can directly put it into the equation, or if Fs is given, you have to calculate capital T and you have to put the capital T in the equation. Okay. However, in some cases you will find in questions in numericals, capital T is not given. In such a case, you have to assume capital T is equal to 1 second. Capital T equals to 1 second. Okay. So now if you look into this transformation equation, so from here what we get, if we find out the pole of the analog domain, the pole is present at s equals to pi. Okay. On the other hand, from the digital domain, we can say we are having 1 minus e to the power pi t z inverse, but for the calculation of the poles and the zeros, what we have to do? We have to multiply both the numerator and the denominator with the highest power of the z. Okay, so over here it is 1, so we will be multiplying both numerator and denominator with z. So that would give us z, this will go off and we will be having z. Okay, z by, so we get z by z minus e to the power pi t. Okay, so if you equate the denominator with 0, we get z is equal to e to the power pi t. Okay, so if you see the location of the pole at s equal to pi, it is been directly given to the location of the pole in the z plane. Okay, so that's how you get the location of, you get an interrelationship between, or the not the interrelationship, sorry, you get the relationship between the analog pole and the digital pole. Okay, now next we also know that s is equal to sigma 1 plus j omega 1. Now here I have used another omega, which I have already told you. This omega is corresponding to the analog frequency. Okay, so if you are dealing in anywhere, if you are dealing with two frequencies, that means the analog frequencies and the digital frequencies, the ohm sign, that omega, it corresponds to the analog frequency, and the omega which is being represented by the this W this thing, it is being represented, it is representing the digital frequency. Okay, so the first omega, it corresponds to the analog frequency, the second omega, it corresponds to the digital frequency. Okay, now if you compare these equations, S equals to Pi transforming to Z equals to e to the power Pi t, we can say this point Pi, it is present in the S plane. So we can rewrite this equation into this form, Z equals to e to the power st. Now see, that's what I have done over here. Z is equal to e to the power st. Okay, but we have just seen that S is given by sigma 1 plus j of omega 1, right? Now if this is the case, let's replace this S over here. So we get e to the power sigma 1 plus j omega 1 t. Okay, now if we just break this down, we get e to the power sigma 1 t multiplied by e to the power j omega 1 t. Okay, now this is the real part and this is the imaginary part. So these have been present in the polar coordinates. So it is in the form of r phase of theta. Okay, so it can be written as you can write it down, r into e to the power j theta form, right? Now from here, if you see the r, which is the real component, it is given by e to the power sigma 1 t, right? And the phase component of the z, it is given by omega 1 t. Okay, now first let us take the first equation, the modulus of z equals to e to the power sigma 1 t. Okay, now depending upon the values of the sigma, we can have three options. The first one is sigma 1 is less than 0. In S plane, when is sigma 1 less than 0? When we are in the left hand plane,
left hand side.
right? Then when we are having, then the case is, the second case is when sigma 1 is equal to 0. So on that case, when sigma 1 is equal to 0, the sigma 1 is equal to 0 when we are on the j omega axis. Okay, and lastly, we have when sigma 1 is greater than 0, which is outside of, which is the right hand side of the plane, S plane, this one. Okay, so let's see what happens in the Z plane. So we are having this Z plane. So when sigma 1 is less than 0, what is happening? E to the power say 0.5, it would be less than 1, modulus of Z would be less than 1. So the left hand side plane of the S plane will be mapped within the unit circle. When sigma is 1 equals to 0, what will happen? E to the power 0 t, e to the, that comes out to e to the power 0, which becomes 1. Then this imaginary axis will be mapped onto the unit circle, right? And the right hand plane, when sigma is greater than sigma 1 is greater than 0, which corresponds to the right hand plane, it will be greater than 1. That means the right hand side plane, it is mapped outside the unit circle. And this condition we have previously also we have discussed, and we can see that if we select an analog filter which is stable in nature, then the digital filter, if we design it using the impulse invariant method, it will also be stable in nature all throughout. Okay, because if you see, we have under all the circumstances, we are having the left hand plane being mapped within the unit circle, right? And in analog domain, if you place any poles within the in the left hand side of the plane, that would result to a what you call stable analog filter or stable system. Okay, now when we transform it into the digital domain, in our FIR class also we have talked about that would result, if all the poles are within the unit circle, that would result in the formation of a stable digital filter. So we are getting a relationship over here that if all the poles of the analog filter, they are present on the left hand side of the S plane, then they will be mapped within the unit circle of the Z plane, which is a must for designing a stable digital filter. Okay, so under these circumstances, we can tell that if we have a transfer function of a stable analog filter, then if we use this impulse invariant method to design the digital filter, then the digital filter will also be a stable filter. Okay, any doubt till now?
No, sir.
Great. Now if you see, we have already discussed that if we have a stable analog filter, we will get stable digital filter. Okay, that's great. And these two equations we have also discussed. Z equals to R into e to the power j omega. It can be Z can be represented in this form. Also, we have seen that Z can also be represented into e to the power st form. Okay. Now, if we compare these two Z's, what we get? R into e to the power j omega is equal to e to the power sigma t multiplied by e to the power j omega t. Okay. So, if we correlate these complex terms, from here we get e to the power j omega is equal to e to the power j omega t, right? Now under these circumstances, if you compare this equation and this equation, so what we get? We get omega, which is basically the digital frequency. It is equals to omega, which is the analog frequency, multiplied by t. Okay, so here we have got this equation, omega equals to omega t, and we can rewrite this equation as analog frequency is equal to omega by t. If you see, we have omega equals to omega by t. So what does these two equation provide us the relationship? These two equations provide us the relationship that omega, which is the analog frequency, is directly proportional to the digital frequency. However, if you remember correctly, we have discussed previously that the analog frequency, it may vary from minus infinity to infinity. It may vary from minus infinity to infinity, right? Whereas our digital frequency, it can only vary from minus pi to pi, right? So what does this indicate? This indicate
So infinite duration to finite duration.
it's not about duration. We are talking about frequency. So how come the duration comes into the picture?
Uh, I think infinite in response to finite response.
What do you mean by response? Response is also, there can be the different response. It is not response also. It is not the response of the filter. So what what is happening over here? We have discussed that analog frequency, it is varying from, it always varies from minus infinity to infinity. Okay, so first let us start with the analog frequency 0 to infinity. For the sake of simplicity, we will take this one first. So under this condition, what is happening over here? We are starting at DC frequency, which is having the 0 frequency at the angle 0 degree. Okay, and then we are going on increasing the analog frequency. So with that, our digital frequency is also increasing, and we get to a point FM where we will be having the maximum frequency. But leave it aside. So further, if we go on increasing the analog frequency, our digital frequency will increase, and we will come to a position of 2 pi, which corresponds to the DC frequency, right? Now under these circumstances, if you further go on increasing the analog frequency, what will happen? From at 2 pi you will be having the Fs, and at DC also you are having the same point. So your Fs and your DC frequency, they will lie on a same point. That means two frequencies, they are lying on the same point, right? Then if you again increase, say Fs by delta, Fs plus delta, it will lie at a point 0 plus delta, right? Again, if you go on increasing this thing, you will come to a point 4 pi. So you will be having 2 of Fs and DC frequency, they are lying on the same point. Similarly, again, if you go on increasing, you will find 3 of Fs, Fs, 2 Fs, 3 of Fs, it will again be lying at the same point. So if you see, there are many frequencies which are mapping to a single point, in the Z transform. Similarly, if you go on in the negative side domain, you will be having the same thing. So if you start from here 0, so if you go on negative frequencies, you will be having the negative frequency domains, and it will be moving in the opposite direction, but the principle remains the same. Okay, so what we are having a condition where many analog frequencies, they are getting mapped into a single analog frequencies. Okay, so which we call it as the overlapping of the frequency. That means many analog frequencies are being mapped into a single point. So if that is the case, then this overlapping of the frequencies, they are regarded as aliasing. Okay. So uh, in news channels and especially in the English news channel, you must have heard that this criminal is um, uh, he's having an alias of this name and whatever. So what is this name? So one person, if he is being called by different names, then that is called alias. So similarly over here, since one digital frequency is being what you call mapped due to the multiple frequencies, we are using this term aliasing. Okay, so any questions till now? No. Okay, good. So to prevent this condition, what we have to do while we are designing the digital filters using the impulse invariant method, we have to band limit the analog frequency component. We have to limit the analog frequency component to FM, so that the other frequencies, they do not come into the picture. Okay, so after then how do you get to a FS? If you band limit FM, then how you get to FS? Because in this digital domain, you have to have the FS component also. So can anyone tell me why we are getting FS even though we are band limiting the analog frequency to FM? Anyone?
So ಇದನ್ನಲ್ಲಿ ನಿಖುಷಿದೆ ಡಿಪೆಂಡ್ ನಿಖುಷಿದೆ ಇರ್ತದೆ.
Nyquist state is different. Anyone? I said we are band limiting the analog frequency, but still then we get FS in the frequency of the signal. How come? बोस जी हैं? नहीं है बोस जी? कौन कौन है? यस जॉयदीप सरकार.
Yes, sir.
Yes, tell me. अच्छा, repeat the question what I have asked. Jyodeep Sarkar, repeat the question what I have asked. Adarsh, repeat the question whatever I have asked.
Hello, sir.
to pro- uh,
Yeah,
Hello.
Joydeep. Yes,
So,
Joydeep. Are you going to tell? No. Okay, others, tell me. What is the question?
to prevent the aliasing, we are actually band limiting the analog frequency to FM,
Hmm.
uh, but we are getting also FS in the Z plane.
Okay. Ask the madam, is the
So,
question correct? So she is also not there.
So, you,
Yeah, tell me. What
so
is the
you asked
question?
that if we bandwidth the signal, then how come we get the FS frequency?
Yeah. So do you know the answer?
So, no.
No. Nilanjan, do you know the answer?
No, sir. No idea.
No idea. Jetal?
Yes, sir.
No. That means you are not studying. The simple thing. We have already discussed that after you band limit the signal, you go for the sampling. And when you are doing the sampling, there is frequency modulation. At that instance, during the sampling, apart from FM, your FS is also added. So even though you are doing the band limiting, when you are doing the sampling, this FS component is getting into the picture. Am I clear?
Yes, sir.
So any doubt? No. Good. So this is a very basic question. So we are having the signal. Before digitizing, we have to band limit the signal. Okay. Once you have band limited, you have fixed up the FM over here during the band limiting, right? Now, to maintain the Nyquist criteria, you are sampling the signal with FS. Now, at this instance, when you are sampling the signal, the FS is getting incorporated into the discrete signal. Okay, and then you go for the this quantization to make the signal digitized signal, right? So since band limiting is happening before you are doing the sampling, due to that reason, in the digital signal, even though we are band limiting the analog signal to FM, we are getting FS in the signal. Okay. Now, important transformations in the using the this impulse invariant method. The first one we have already discussed. If you are having we are having distinct poles. The second equation is 1 by s plus pi to the power n. It is given by this equation, this transformation equation. So this equation is valid when we are having multiple poles. Here, one of the important thing what you have to remember is that we are having plus over here, whereas in our previous case we have discussed s minus pi. So that you have to take care. So if you have s minus pi over here, that means in some equation you have s minus a. That means it would, you should consider it as s plus or minus a, and then wherever so minus a means this pi, so this pi will be replaced with minus of a and not a. Okay, so keep these things in mind. Similarly, we have this third and the fourth equations for the complex poles. Okay, so these are the equations. These two are the equations: 1 minus e to the power at cos bt z inverse divided by 1 minus 2 e to the power minus at cos bt z inverse plus e to the power minus 2 at z to the power minus 2. And similarly, this b by s plus a whole square plus b square, it transforms into 1 minus e to the power minus 80 sin bt z inverse divided by 1 minus 2 e to the power minus 80 cos bt z inverse plus e to the power minus 280 z to the power minus 2. Okay, so these are for the complex poles if you are having complex pole. Now let's see, look into some examples. So suppose we are given with that we are given with the transfer function of an all pole filter. Okay, and this example has been taken from S Palani, digital signal processing by S Palani. So this analog transfer function, it is given by hs equals to 1 by s square plus 5s plus 6, and this can be broken down into s plus 2 and s plus 3. However, we have to get into this form, so we have to apply partial fraction. So a by s plus 2 plus b by s plus 3. Now if you calculate these values, we get this equation. Now once you get this equation, as I said, here the equation is s minus of pi. So we have broken it down into s minus of minus 2 and s minus of minus 3 to apply this transformation equation. Okay, so we have applied the transformation in the equation. There is no information about t. Just a few moments back I have told, if nothing is given, then t, you have to assume that t is equal to 1 second. You just put these values over here: 1 minus e to the power minus pt, okay, e to the power pt. So here p is minus 2t z inverse. Similarly over here minus 3t z inverse. Okay. Now t is 1, so it goes off. Now just put the values and you get this equation. You can further simplify this equation and you can go for the realization of the filter. Okay. Similarly, the next equation, the next question, we are given with an analog filter transfer function. Okay, and we have to convert it into digital filter by impulse invariant method, and here it is given that t is equal to 1 second, and this question is also, this example is also from the S Pelani book. Okay, so what you have over here, this hs equals to 1 by s plus 3 minus 1 by s plus 5, again by the partial fraction method. Just change the put the values over here and you get to the equation. Okay, then the next question is from Ramesh Babu. So hs equals to 10 by a square plus 7s plus 10. Here t is given as 0.2 seconds. Now in this case, if you see, while putting transfer functions over here, what I have done, I have given a, I have added a multiplier of capital T, and this multiplier of capital T is added for high sampling rates. Here your T is equal to 0.2 second. So usually if capital T is regarded as is less than 1 second, is less than 1 second, then you can include this equation also. Okay, so here whatever the equation we have put, it will be multiplied by capital T. Okay, in case we are having very high sampling rates, so this multiplier should come into the picture. Okay, then you solve the question in the similar way. Okay, now next is convert the analog filter with system transfer function h is equal to s plus 0.1 divided by s plus 0.1 whole square plus 9. This question is also from S planning. Okay, so into a digital filter by using the impulse invariant method. So if you see, it is in the form of s plus a divided by s plus a whole square plus b square. Okay, so this fourth equation you can directly put values over here. Otherwise, what you can do is that you can solve it in this fashion. So these will be formed into these complex domains A1 and A1 conjugate. If you see A1 S minus this minus of 0.1 plus J3, and this one A1 conjugate divided by S minus minus of 0.1 minus of J3. So if you look into this fraction and this fraction, they are conjugate to each other, and also this numerical part, it would be conjugate to itself. By the partial fraction method, you have to calculate the values. Okay, and once you have calculated the values, you apply the impulse invariant transformation method to calculate the exit. And whenever you get these values in cos terms, if you see this cos 3 and this thing, so these are in radians. So whenever you will be calculating, you will be putting it into the your in your calculator. Your calculator should be, for the calculation of this function, it should be in the radian mode. Okay, are you getting my point? Hello.
Sir.
Yeah. So
Yes, sir.
yeah, so today we will stop over here. So if you have any question, you may please ask.
Sir, in case of then designing for impulse invariance method, we first have to check the stability, right?
Which one?
Because, sir, for designing this using this method, we have to first check the stability. Then, suppose there is a pole in the right hand side of the S plane, then the filter cannot be designed.
Yeah, in any of the cases, in whatever the digital filters you will be designing, you will be given with the analog transfer function. So uh, it is assumed that while you are giving this numericals, that the digital filter will that the analog filter will be the stable filter. Okay. However, whenever you are going for this mm, designing of the filter for your what do you call, for your research application, then you have to check all the things. However, for the exam purpose, for the this classroom teaching purpose, whatever the filters will be given, you can expect that all the filters will be uh, stable filters. Otherwise, how will you solve the numericals? Are you getting?
Yes, sir.
Yeah.
So after Hz, we have to put Hz equal to Yz by Xz, then we have to realize the filter, right? The last step.
Yeah, if it is given that realize the filter, then you have to solve it further, solve this equation further. Okay, and then you have to convert it into xz and yz terms. Okay,
Okay,
because
sir.
the realization of the filter, I have told you, that is a simple method, but it is a altogether another is altogether a separate topic. There are 3 or 4 methods: direct form 1, direct form 2, then cascade realization, parallel realization. So that we'll be discussing in a later chapter. That's why I have not gone into the details, but I have already given you an example how to go for the realization of the filters in a simplistic manner. Okay, so just by looking into the equation, if someone asks you to go for the realization, so you can do the realization, right? The performance of these filters can be bit involved, can be bit improved. If you see over here, I have used 3 adders, okay, because there are 1, 2, 3 additions are there. However, if you see, all these are being added up, so I can just change it to XZ. I can replace with 2 adders, B minus of A. So this will also be giving you the same answer, but if you see, uh, I have been able to remove one of the adders, so one computation will be lower. So this one is better than the previous one, but at least you can realize a filter uh, until we get to the point where we'll be discussing the realization of the filters bit in depth. Okay. Anything else? Oh, sorry, in this equation, I did a mistake. See, this is s plus a divided by s plus a whole square plus b square. No? So, if you see, this third equation will be used. Sorry. Okay. So, it is in this formula. So, that's why if you see, it is getting cos bt over here. Here also, we are getting this cos and cos terms, right? So if you have no other questions, we can stop.